So our topic, this unit, is work, energy, and power. And again, it's going to be mostly review from Physics 11. Oh, but we'll throw angles in now as well, because we can, hey, go 2 dimensions. Okay. This unit, generally, kids find mathematically a little easier, because almost everything in here is a scalar, which means you're not doing all that much vector math. You're not adding things tip to tail. Most of the time, you're going straight to your calculator. Oh, but first, turn your paper sideways. We have a lovely little question for us to answer up here. Yep. In 1977, in Northamptonshire, England, David Purley's race car crashed and his speed dropped from 174 kilometers per hour in 0.66 meters. He had 29 fractures, 3 dislocations, 6 heart stoppages, but he survived. In fact, as far as I know, this is in response, a kid asked me this a few years ago, so I looked it up. As far as I know, this is the person on record who survived the biggest deceleration, the most G-forces. Permanent damage, but he survived. How many G's did he experience? Hey, what's this question asking me to find? Well, G's, we're going to start out finding the accelerations. I'll put A equals question mark. What do I know in this question? What's VI? 174 what? Ah, I can't do math with kilometers per hour. How do I go from kilometers per hour to meters per second? Can someone divide by 3.6 on their calculator? I can't bring my calculator up. It won't flip. It'll be all sideways, but I can flip the screen, which is nice. Sorry? 48.33? Yeah, is that right? What else do I know? What's VF? Yes, I do. And I know one more thing. What? 0.66. By the way, putting that in perspective, so 174 kilometers an hour, that's almost twice as fast as freeway. And he went from full speed to 0 in, that's about 66 centimeters right there, right? Because a meter is like this. Well, just more than 2 rulers, because a ruler is 30 centimeters. So 66 centimeters, a ruler, another ruler, and a bit. Yeesh. I'm looking for an equation that has A, VI, VF, and D in it. Can you get the A by itself for me, please? A equals? All right. Hey, crunch the numbers. Find the spectacular acceleration this person experienced. David Purley. I think you get a number in the thousands. You'll get a negative because he is slowing down. Yes, should get he's decelerating. Should get a negative. 1,946 or 1,846? Is it? Okay, 1,767. That sounds better. 1,000. But negative, yes? Now, I didn't ask you what the acceleration, I said how many G's. If I know the acceleration, how do I change that into G's? It's actually really quite simple. Divide by 9 point. How many 9.8s go into there? Because when they talk about G's, that's what they're talking about. They're taking the acceleration and dividing it by 1 G. They say G force, they really should say G acceleration. Divide that by 9.8. How many G's did he experience? Putting that in perspective, on the elevator, you experience about 3 G's. 180 G's, well, that would be like 180 people dogpiling on you all at the same time. Not pleasant. But as far as I know, this is the biggest survival. I'll do some more research. It may have changed since then, hopefully not, because cars have gotten safer. You'll notice this is in 1977. How can we lower the G-forces? Well, we can't really lower V initial because they want race cars to go fast. We can't change V final because all crashes end in a stop. What can we change there then?
Time.
There is no time in there, but it's related though. Yeah, the distance. You know what we do? We build crumple zones into the cars so that hopefully part of the car crumples first, slowing you down before your body runs into whatever. We have some personal experience with that here. We lost a former student a few years ago, Greg Moore, in a racing accident, right? So we're interested in some of this in our school. All right, now let's start. Work. We got a problem with the word work. The problem with the word work is it means something in English. For most of you, when I say work, you think getting tired. Work has nothing to do with getting tired. Well, it does in a roundabout way. But when I ask you, are we doing work, don't you think, oh, am I getting sweaty? Am I getting tired? It has nothing to do with that. In fact, work has a definition. It's a scalar. Woohoo! And it's defined as the product of the force component in the direction of motion. I underlined that for a reason. And the distance moved. In other words, work done by a constant force is given by you may notice I've dropped the vector notation. It's a scalar. The key here, Jaron, though, is the force and the distance have to be in the same direction. They have to be. What are the units? Well, force is measured in newtons times. Distance is measured in meters. It is a Newton meter, but we've given that a special name. Anybody remember what we call the unit of work? Joules. Symbol J. Named after a scientist whose last name was Joule. So, little illustration of what we're talking about with work. So for those of you watching at home, I just had one of my students give another student a piggyback, and we said, when you're moving horizontally, carrying something to resist gravity, you're not doing any work on that object because the force is vertical and the distance is horizontal. Example 1, how much work do you do when you lift a 35 kilogram mass to a height of 1.5 meters? Well, first of all, let's write down our definition of work, which was force times distance. Key word here is lift. When you lift something, which force are you opposing? And you know what? We could put a D there for distance, but since they used the word height, what would be a clever letter to use there instead? And we called this last year potential energy. This is where the potential energy equation comes from. Anyways, mass 35, G 9.8, no negative, it's a scalar. Height 1.5. How much energy would your body give up? How much work does it take to lift a 35 kilogram mass to a height of 1.5 meters? 515, because you went to 3 or 2 sig figs. 550, is it 515?
Yep.
35 kilograms, is that a lot? How many pounds is 35 kilograms roughly? About 75 pounds. So you know what, let's put this in perspective. This would be the equivalent of bench press, well, picking up from the ground, 1.5 meters right about here, a 9 or 10-year-old kid. Right? They usually weigh around 75, 80-ish pounds, give or take. Is that easy? Well, all of you could do it. In fact, in an emergency, all of you could probably do it on an adrenaline rush several times. If I asked you to do it 50 times in a row, all of you would be getting pretty tired. And the reason I'm doing that, so 515 joules, Jake, not a lot of energy, enough energy that a little oomph is required. I want you to get a feel for what these answers look like, so when you're actually solving a question, you can glance at the answer and you can say, that's way too small, I've done something wrong. Or that's way too big, I've done something wrong. So 515 joules, very doable. Example 2, how much work does a hiker do on a 50 kilogram backpack? That's a heavy backpack. If he carries it to the top of a 750 meter mountain. 50 kilograms, you know what? That's probably, well, that's about 130 pounds. So now let's think you're piggybacking someone who's reasonably lightweight instead of a backpack. Carrying them 750 meters straight up, whether it was on a slant or whatever, would that be tiring? Okay, how much work? Once again, work equals force times distance. which is going to be mass, no, not 50, 50, times 9.8 How big? Jake, what'd you get? It's in the 300,000s, yeah? Oh, I thought you went, oh, like it was a big number. Sorry. Jaron, what'd you get? So 3.68, is that right? Times 10 to the what? Joules. Now, I can choose to do this work all at once. That would be carrying somebody, let's say, on your shoulder up a 750 meter high ladder. That would be very tiring. Or I could go up a really shallow ramp. It would take longer. It would be less tiring. And this is sort of what Jaron was kind of wondering about when he brought in time earlier. What we think of as tiredness really is power. Power. That's why we use stairs instead of ladders. It's less tiring to climb stairs than climb ladders. It takes more time. You spread the work out over a longer amount of time, which means your body can deal with it easier. Oh, and if I need to, make the ramp longer and shallower. But that's another lesson. Example 3, a ball on the end of a rope is following a circular path with a constant force. In fact, you know what? I'm talking about this. So I'm whirling a ball around my head on a string. How much work am I doing on the ball? Well, according to the question, what direction is the force? Inwards. What's the distance that this ball is traveling? Inwards? So under our physics definition, how much work am I doing on the ball? If the direction and the force are not in the same direction, what does that mean? Jaron? 0. 0. You know what? That's confusing enough that we're shortly going to give you a better definition of work. In general, if we're moving in a nice straight line, Taylor, a force in the direction of motion, like F1 on the next page, we say it does positive work. A force in the opposite direction of motion, like F2 on the next page, we say it does negative work. That doesn't imply a direction. What it really means is if you did negative work, the object lost energy. It lost energy. So, although work can be positive or negative, it's not a vector. Negative work does not mean to the left or down. Negative work, Chelsea, means you lost some energy. Or positive work means the object gained some energy. What about the lawnmower question? Example 4, a child is pulling a wagon along the driveway, exerting a force F along the handle of the wagon. How would you calculate the work done by the child on the wagon? So here we have a horizontal displacement. And we have a force at an angle. Well, what do you think? We kind of handled something similar with the lawnmower problem last unit. Components. Components. What I would do is I would say, okay, here's my force F. If my distance is horizontal, I would use the horizontal component if I knew that angle. In fact, I would get this. Work equals Fx times distance. Oh, F is hypotenuse, yes. Fx, adjacent or opposite. There's my angle right here. Adjacent or opposite? Which trig function? In fact, really, the proper definition of work, the one that you'll use next year in university, is that. It's force times distance times the cosine of theta. Oh, and if theta is 0 degrees, hey, what is the cosine of 0 degrees? 1, which means it just vanishes and you get force times distance. Oh, what if theta is 90 degrees, like when Jaron was piggybacking Terry? What's the cosine of 90 degrees? 0. Which means no work. By the way, I fibbed a little bit. I said, well, this is what you'll use next year in university. No. You see, next year in university, you'll also ask yourself one more question. You'll say, what if the force is not constant? What if it's a changing force? And what you'll do is you'll bring in the calculus version of this. Now, the calculus version of this says the integral of a tiny amount of work, don't write this down, is equal to the integral of your changing force times the distance times the cosine of the angle. That's calculus notation. Who's in calc? You're just starting to do derivatives? Yes? Just starting, yes? Once you learn how to do derivatives, towards the end of the year, you'll learn integrals. An integral is, if I know the derivative, what equation did it come from? That's the integral. So that's that symbol, that's that notation right there. It's much easier than it looks and much harder than it looks at the same time. For now, we don't have calculus. So what if the force is not constant? Jaron, work is what times what? That's definition number 1. I'm going to end up giving you 3 definitions today, and I'm going to teach you how you can figure out which definition to use when you're solving a question. The second definition is this. Work is also the area under, and then cross out the word of. It's the area under a force versus distance graph. You know how I know when to use this one? Oh, they gave me a graph in the question, which may sound obvious, but I'm telling you. What kind of a graph? Force versus distance. How can I remember that's the area under a force versus distance graph? Jaron, force is equal to what times what? No. What did you say? I just asked it to you 30 seconds ago. Force is equal to what times what? How can I remember that it's the area under a force versus distance graph? That's the also amount of work. Force is equal to what times what? Oh, okay, I got to tie in there. So the whole concept that it's the area under a graph, not on my formula sheet blatantly, but it's in the equation, sort of. So here's a question. My F got chopped off for some reason. Apparently yours did not. Is that right? Force in newtons versus distance in meters. And I asked you, how much work is done moving this object from 2 meters to 6 meters? You may notice that the force is not constant, because at 2 meters the force is this high. At 6 meters the force is this high. It's a changing force. Force is what times what? Can't use that. Force is also the area underneath a force versus distance graph. Hey, there is a graph here. What we really are talking about is that area. Anybody, what shape is that? Oh, I heard it. Jason. Trapezoid. It's a trapezoid. Jason, for a candy and my undying respect, do you by chance know the equation for the area of a trapezoid? It's not on your formula sheet because you don't need it. I'll tell you why. But holy smoke. Where'd you pick that up from? Were you taught it? Around. Oh, Jason. Jason. You know what? I'm going to see if I got a toonie in my pocket. I'm going to give you the toonie. Oh, I didn't put the toonie that was sitting on my dresser table in my pocket, did I? I didn't. All I can give you is a candy. By the way, there's a reason why we hardly emphasize it. You can get away without it for the most part. And John, you can get away without it by recognizing, you hope. It's a rectangle and a triangle, both of which we have taught you the area formulas for. So if I want to find the area underneath this graph, the work is going to be the area of the first shape plus the area of the second shape. The first shape is a rectangle. What is the equation for the area of a rectangle? I think depressingly this is on your formula sheet. I really don't think it should be, but I think it is. Anyways, what is it? For a rectangle? Length times width plus. And what's the area for a triangle? Jaron said length times width, although traditionally we say base times height divided by 2. So let's look at the bottom rectangle. How long is it? Don't say 6. 4. How wide is it? 2. That's supposed to line up with the 2. It sort of does. Plus. Look at the triangle. How long is the base? 4. What's the height of the triangle? Don't say 3. 1. Divided by 2. Don't you dare reach for your calculators. What's 4 times 2? What's 4 times 1 divided by 2? What's 8 plus 2? Someone said 6? Wow! I'm sorry. I have to make a little bit of fun of that one. Although you got perfect on the test, so no problem. Okay? You can expect somewhere on your test, I'm going to give you a question that involves work and energy. I'm only going to give you a graph. No, it's going to be the area underneath said graph. It's not going to be a weird, funky, curvy graph. By the way, one of the reasons calculus was invented was to deal with, hey, what if you have a force versus distance graph, and the force does that, and you want to know how much work that took. What's the formula for the area of a curvy shape? Okay, and there is one, by the way. No, who's in calc? Probably around May 15th. Integrals is always the last thing you do. So we talked about work. Jaron, work was what times what? I'm going to keep coming back to that, okay? It's also the area under a force versus distance graph. Energy. Now that we've defined work, this allows us to define energy. Energy is the ability to do work. It's the ability to exert a force over a distance. For example, if I were to drop this on Jason, I won't. If I were to drop this, would it exert a force over a distance when it hit his skull? Yes. So does this possess energy? Yes. More energy or less energy? Did I do more work or less work? More. Okay? In fact, we gave this particular energy a name. We called it gravitational potential energy. All right, I've had it enough. Terry, you're sitting there. I can play piano. I'm going to throw this at you. I'm going to throw this at you as hard as I can. It's going to hit you in the face. When it hits you in the face, will it exert a force over a distance? Yeah. If it's moving, if I throw this at you, does it possess energy? Yeah, because it has the ability to do work. There's all sorts of types of energy. Many types. For example, there's the energy of motion. Do you remember we gave that a special name last year? What have we called the energy of motion? Kinetic. Heat is a form of energy. Oh, by the way, I've turned the page. Wow, all of you just now. Okay. Heat is a form of energy. Heat is, well, it's all created by friction. Really, Mr. Duick? What about like in a stove? Friction between the atoms in the element rubbing against. Trust me, everything comes down for heat to friction. Gravitational potential energy, as evidenced by the huge weight that I held over Jason's head. Chemical potential energy. Potential energy, by the way, is stored energy. So chemical potential energy, like gunpowder, gasoline, the fuel that you eat, the food that you eat, all has chemical potential energy stored in it. Sugar. Other forms, sound is a form of energy. Elastic energy is a form of energy. Nuclear energy, stored within the nucleus of the atom. Elastic energy in a slingshot or a bow and arrow is another great example. Lots of types of energy. In this unit, we're going to be looking at three main types. Heat, but we're not going to calculate heat. We're going to find it indirectly, because to calculate heat, that's actually, you need like specific heat capacity of the object. Heat's a very, very difficult topic. But the other two main types that we're going to look at are what are called mechanical energy. We break them down into kinetic and gravitational potential. So, example 4, sometimes when we do work, we make things move. Fill in the proof below to find an expression for motion energies. Anybody remember the equation for kinetic energy? Mabad. It's going to be down here, a half mv squared, and it's a scalar. I'm a nerd. I'm going to walk through the proof with you. You don't need to know the proof, Chelsea. I just can't resist. We're going to start out with our definition of work. Jaron, work is what times what? And from last unit, F equals what? MA, the more generic, right? In fact, it's MA times D. And now I'm going to get clever. I'm going to rewrite this. I'm going to leave a space in front of the M. I'm going to put the M there. I'm going to leave a space. I'm going to put the A and the D together. And then what I'm going to do, Gabby, is I'm going to put a 2 right here and a 1/2 right there. If I multiply by a half and I multiply by 2, what do those two do to each other? So I haven't changed the question, but there's a reason I've done that, because do you know what 2AD is if I go to VF squared equals VI squared plus 2AD? What is 2AD the same as? I think it's the same as VF squared minus VI squared. Wasn't that clever? Oh, and Gabby, if we start from rest, what's VI? If we start from rest, and can you see we have a half m v final squared? That's where it comes from. There's all sorts of other derivations, but there's one. You want to find out how much motion energy, kinetic energy, an object possesses? It's a half mv squared. It's a scalar. Oh, I was Googling trying to find different energy values. For what it's worth, one jelly donut has 10 to the 6th joules, and one mosquito push-up, I kid you not, has a name. It's called an erg, and it's 10 to the negative 13 jelly donuts.
How do you measure that?
Pardon me?
How do you measure a mosquito push-up?
You probably go force times distance, which is mass times acceleration times distance. You would know the mass of a mosquito. I'm sure they have that somewhere. G is 9.8, and you would know the height of a mosquito's legs. That's how much a push-up would be. Since you asked, it's MGH, my friend. Right? All right. I've been helping out with the golf team for the last couple of years. Apparently, by the way, this year we have a grade 9 exchange student from Japan, a girl who competes internationally. You guys saw this summer an amateur won the Canadian Women's Open here in Surrey. This girl has played against that girl apparently, and is going to be better in all this. It's great. Anyways, back to here. A few of you are involved with the golf team. A golfer wishes to improve his driving distance. What would have more effect, if I double the mass of my golf club, or if I double the speed with which my golf head strikes the ball? And convince me. Jason, speed? Why? Jason, what? You're on a roll, huh? Say it louder. Basically, louder.
Yeah, the equation is 1/2
When I say louder and you start out loud and you just start tailing off, for example, and then if you double the B, you're right. But I just want to, you know what? How would I write that up? You know what I'm going to do? Maximum bang, minimum work. I'm going to go like this. Donk. Line in the middle. I'm going to say, okay, there's two possibilities. Double the mass, double the V. And let's write out kinetic energy equals a half. Now, if I doubled the mass, I would put a 2m, and I'd have a v squared. Yes? And this is Jason's argument. This is how I'd formalize it. Jason, what does this simplify to? Well, you have a half and a 2. What happens to those? It simplifies to mv squared. Now what if I double the velocity? I would get this. Kinetic energy equals a half m. What if instead of a v, I put in a 2v squared? You get a 4 times a half. You get a 2mv squared. Oh, circle B, therefore B. How has that affected the past 15 years? You may have noticed in the past 15 years, all sports equipment has become, what, heavier or lighter? Why lighter? You lose some of the mass, I recognize, and I mean, mass does also increase kinetic energy, but where do you get way more bang for your buck? Club head speed, hockey stick speed, baseball bat speed, tennis racket speed. Tennis rackets is the classic ones. I played tennis growing up, and I started out with a wooden racket, and every once in a while I'll watch, like on ESPN Classic or something, an old match from the 70s. It's painfully slow. What, were they just lousy athletes back then? No. In fact, some of them might even have been better athletes than we have today. It was the equipment. Yeah, okay, the training is a bit better today. They do a lot more weightlifting and things today. It's the equipment. It's the equipment. It's the equipment. So, kinetic energy. Example 5. Sometimes when we do work, we lift an object and give it height energy. Stored energy based on an object's position or distance from the Earth's surface. We call it gravitational potential energy. It says, fill in the proof below to find an expression for height energy. Okay, work equals force times distance. If you're lifting something, it's mg. And if it's a vertical distance, we call that a height. The mgh we already derived in the very first example way back when. It kind of pops out naturally. I should be fussy. Josh, this only works close to the Earth's surface. Out on the space shuttle, G is not 9.8. So in a couple of units, we're going to go cosmic, and we'll come up with a potential energy equation that will work anywhere in the universe. But it's a lot more complicated and cumbersome. Okay. Can you have negative potential energy? Sure, dig a hole, drop something down there in the bottom of the hole. Now it's got negative potential energy, because to get it back to zero, you'd have to do some work and lift it up to get it back to zero. Usually we focus on mechanical energy, which has two main types, kinetic and potential. Jaron, work equals what times what? It's also the area under what kind of a graph? Area, Jaron, stop, don't turn the page. Work equals what times what? It's also the area under what kind of a graph? I'm going to say force versus distance graph, but yeah. Okay. There's a third definition of work. This is actually the best, most universal one. It's called the work energy theorem. It says this: the net work on an object is equal to its total change in energy. The net work is equal to the change in energy. And for this unit, we're really going to say it's equal to the change in potential plus the change in kinetic. Okay, there might be some heat left over, but I'm not going to include that in this equation. By the way, what's change in anything? This is the reason I brought that up months ago. Final minus initial. So let's go back to when Jaron was giving Terry a piggyback. When they were walking at a constant speed, was Terry's height changing at all? So was his potential energy changing? No. Was his speed changing at all once they started moving? So was his kinetic energy changing? No. So was Jaron, in terms of physics, doing any work on Terry? No, because Terry was not gaining or losing any energy. Oh, in fact, because Jaron and Terry were staying on the same height, you could simplify the work energy theorem, and sometimes I've seen some textbooks to give it this way. They've said the work energy theorem is equal to the change in kinetic. I don't like that. That's wrong. It's not the change in kinetic. It's the change in potential plus the change in kinetic. Except this unit, most of the time, You're going to be starting on the ground and ending on the ground, so the change in potential is going to be 0. But when we go into outer space, you won't be ending on the ground. Then we'll have to bring in the big version here quite a bit. February. Example 7. How much work must be done to stop a 1,200 kilogram vehicle traveling at 32 meters per second? Chelsea, what's this question asking me to find? Work. Jaron, work is what times what? Look at this question. Do you see a force or a distance mentioned anywhere? No. So I know Jaron's method's not going to work. Oh, it's also the area under what kind of a graph? Is there a picture of a graph here? Nope. Do you see, you use a process of elimination. When do I use the work-energy theorem, Mr. Dewick? Check. If there's a force and a distance, go with that. If there's a graph, go with that. Otherwise, change in potential, change in kinetic. That's how you know when to use this one. This one, by the way, not on your formula sheet. Someone last class said, can we add it to our formula sheet? No. No. If you do the homework, you'll end up memorizing it. How high is this car when it starts? I think 0. How high is it when it ends? 0. How do I know? Doesn't mention a hill or anything. I think, Tyler, I can say there is no change in potential. Jake, what's changed in anything? You're stretching. I'll wait till you finish your stretch. Now you're done. What's changed in anything? Megan, what's changed in anything? Megan, what's changed in anything? It's not on your sheet. You need to have this memorized. John, what's changed in anything? Jake, what's changed in anything? Megan, what's changed in anything? So what's changed in kinetic energy, Jake? How about kinetic energy final? Oh, one more thing. On your formula sheet, they use, for energy, kinetic and energy potential. I don't like that because 2 units from now, we're also going to be using E for electric field, and they mean something completely different, and kids get them mixed up all the time, and it drives me crazy. Do you have your formula sheet handy? I see the yellow one there. Jake, look at the electrostatics unit. How many different E's do you see kicking around? Should be initial. Yeah, I wrote initial for some reason here. I'll fix that. So Jake, I'm going to use KE and EE because you see all sorts of E's there. So to alleviate the confusion, I'm going to decide to use KE for kinetic energy and PE for potential energy. And I got to be honest, I believe technically that's wrong. Did I say Josh? Jake? I said Jake several times? Wow, good gosh. That's because I'm yelling at Jake over there. I was so disappointed in him. I wanted to give him a chance to succeed, so I went to you. I don't know. Uh-oh, Mr. Dewick, you've hurt someone's feelings. Like I care. Okay, Jake, redeem yourself. What was the equation for kinetic energy? Kinetic energy equals, do you remember? It's on the previous page if you need it. Look it up if you need it.
Too much pressure, I think, for you to stuff out.
Yeah, I know. So I'm picking on you. Yep.
It's a half mv squared.
So it's going to be a half m, I think, v final squared, because it's not the mass that's changing, right? Minus a half m v initial squared. Are any of these 0? What's v final? How do you know? Stopped. Oh, so you're saying the final amount of kinetic energy is going to be 0? So how much work does it take to bring this car to a stop? Negative 0.5, 1200, 32 squared. What do you get? By the way, by far, the most common mistake in this unit, kids forget the squared. Don't do that. What do you get? Mabad?
Negative 6.9 times 10 to negative 5.
So try that again. Negative 6 point what? 6 point?
1.
6.1?
Yeah, 1/4.
1.4 or 1.5?
Negative 1/4.
Times 10
To 5.
units?
Joules.
Joules. Yeah, it's work. By the way, you got your calculator there? Can you go 32 meters per second times 3.6? How many kilometers per hour is this? About 100, right? Okay, so this is saying how much work does it take to stop a car that's going at freeway speed? Would you be able to, with yourself, with your body, stop a car going at freeway speed? In other words, absorbing that much energy all at once would kill you. Although, Dorothy, if I said that you had 10 miles to do it, if you can spread it out over longer, in fact, sure, if you were really, 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 really careful, you probably could, if you were in the passenger seat, open the door and carefully put your foot down, carefully, and actually skid to a stop. Come on in! But you wouldn't want to absorb this much energy all at once. It'd be bad. Example 8. A 19-kilogram artillery shell is launched from a cannon. Boom! At the top of its arc, it reaches a height of 245 meters with a horizontal speed of 95 meters per second. What's the minimum amount of work that the cannon did on the artillery shell? Okay. Alicia, what's this question asking me to find? Work. Jaron, work is what times what? Do you see a force mentioned in here anywhere? I see a height of 200. Yeah, I don't think that's going to go. It's also the area under a graph. Dost thou see a graph here? Nay, thou dost not. Verily. So pray thee, what definition of work shalt thou useth? Work beeth the change in energy of potential. Accoutramented with change in kinetic energy. What's change in anything? So I think I can say it's going to be potential energy final minus potential energy initial plus kinetic energy final minus kinetic energy initial. Sure. Are any of these, well, you know what, let's fill in a bit more. It's going to be mgh final minus mgh initial plus a half mv final squared minus a half mv initial squared. Are any of these zero? Dorothy, what? I think we're going to assume it starts on the ground. We're going to do one more thing. Well, I know the final velocity. What's the final velocity? 95. What I don't know is the initial velocity. I'm not going to say this is 0. I'm going to cross this out, though, and I'm going to say because they're asking for the minimum amount of work, what they're really saying is, you know what? If we don't care about what you left the cannon at, the gunpowder has to give it at least this much energy. At least this much. In fact, if we knew it needs that much energy, we could then say that must have all come from the kinetic. We could probably figure out how fast the initial velocity was. That's using the law of conservation of energy. That's next lesson. Work equals 19 times 9.8 times 245 plus 0.5 times 19 times 95 squared. What's the minimum amount of work that this cannon did? And that's ignoring whatever velocity we left the ground at. It's a canon. I'm assuming it's going to be a fairly big answer. Sorry?
1.31 times 10 to the 5 joules.
Anyone else? 1.31 times 10 to the fifth? Yep. (1.31 times 10 to the fifth joules). Actually, less energy than it took to stop a car. Okay. What's your homework? You can do number 1. You can do 2A and 2B. I haven't done efficiency yet, so you can't do C or D. You can do 4A, 4B, and 4C. I haven't done power or efficiency yet, so you can't do D and E. You can do 6. What happened to number 5? I went same place as number 7, 8. Oh, 3 was missing too. There you go. 10 kilogram mat. Now, I'm going to assign number 9, and I'm going to say to you, I haven't talked about a force at an angle. We have done components. If you don't, I'm going to let you try this. I'm fully prepared to go through this whole question with you when I see you next on Friday. It's a nice way to actually start the next lesson. And number 13. Oh, we got lots of cool videos for this, but they'll all have to wait. Okay. Also, please get any missing assignments from last unit into me.